Welcome to the course Thermodynamics. In this lecture, we will study about pressure and temperature. We will look at the definition, various standards, measurement techniques, reporting and interpreting the measurements and the units. In thermodynamics, we come across many properties. Some of these are listed here, like here there is mass, mass flow rate, specific enthalpy, speed of sound, Joule-Thomson coefficient and many more. But first, all these have a basic requirement that they can be applied when the substance is a continuum. A continuum means that whatever size we take of the material, we have a very large number of molecules and their collective behavior is what is being quantified. So, this is what we have in thermodynamics as the macroscopic approach. We are not looking at what is known as the free molecular regime, where you have just one or two molecules that we are trying to study. So, this can happen in two ways. The continuum, you could take a element like this one, and in that there will be a large number of molecules, not necessarily all of the same type, there could be different type of molecules. And what we are saying is, we are not going to be looking at what each one of them does, but we take the collective behavior, all of them, make some sort of an average and assign that a particular property. So, this is typical in any system. In an internal system where there are bounded walls, this tells us that the size of the spacing between the bounded walls cannot be smaller than a certain distance. So, this is say a channel. These days there is a lot of research going on micro channels and nano channels, which tells you that there is a minimum distance here which is essential for this substance to be treated as a continuum. At the other end, we could have an object like this. This could be a satellite in low level Earth orbit, and around this there are molecules. But at that altitude, there are so few molecules that their mean free path, that the typical distance between them is all of the order of 1 meter, and if this object is 1 meter in size, then we are clearly not in a situation where we can pick up the macroscopic approach. This is not a continuum. So, in thermodynamics, we assume that everything we are doing is the macroscopic approach. We are working with the continuum, and now we proceed to look at its analysis. But of all these properties that we have, and there are many more than this, the question arises, which of these properties can be measured? And we will see in a minute, there are a few properties that we measure, and then we ask the question, how can I get the values of all the other properties? And for that, we go back to thermodynamic relations, knowing that properties are point functions, and we can write differential equations for them, and using that we can then do a whole lot of calculations and get all the other properties that we want. So, let us see which are the properties that can be measured. So, in a laboratory, the direct measurement of the properties that we can do, there are very few. This is dimension, then there is mass, volume, pressure, temperature, flow rate, some cases of flow rate are calculated values, same thing with volumetric flow rate. And others are done by a calculation. For instance, say density or specific volume, this would be done with a measurement of mass and volume. Specific internal energy would require some more measurements, and so on. So, here the two most important properties that come across in thermodynamics are pressure and temperature, and in this lecture we will see what do they mean, how do we measure it, and how do we report their measurements. So, we begin with pressure. The first thing is pressure applicable to every material? And the answer is no. Pressure as a property is applicable always to fluids, gases and liquids within the realm of a continuum. For solids, inside a solid, pressure is not defined. At most, we can define pressure only at the surface of a solid which is in contact with the fluid, and that too on the fluid side. So, what we are saying is that if this is a solid and around this is any fluid, then we can talk of pressure on the surface of this solid, that too on the outside, not just below the surface within the solid. Inside this, pressure is not defined. We only talk of stresses, normal stresses and shear stresses. So, that is an important distinction to make. And then there are many cases which do not fall in these categories at all. For example, a viscoelastic material or something like a paste or a multi-phase system like say a dough, and we ask, well, can I apply pressure and talk of pressure of those systems? In general, we should be very cautious. If both phases happen to be fluids, then we can talk of pressure. Otherwise, mostly the answer is no, although we can ascribe certain number as a pressure for that system. For example, in the case of two fluids, if we say that there is vapor here and inside that there are some droplets of liquid, then the pressure here is going to be the same, and we can talk of the pressure of this mixture of a solid and liquid, of a liquid and a gaseous phase. So, that is an example where two phases together we can talk of the pressure, but there are others where pressure as a concept begins to break down, and we then have to go back to the fundamentals of stresses to figure out how to analyze that problem. In this thermodynamics course, we will not be going into that. So, pressure can be applied when the fluid is in mechanical equilibrium. That means, everywhere in the system the pressure is same. There are no pressure gradients within the substance. Fluid is stationary, or in some cases fluid is in motion with a constant velocity or maybe even accelerating. And even if a fluid is undergoing a process, for instance, it is going through a nozzle and getting accelerated, or it is being heated, we can still talk of pressure of that fluid. And when we say pressure, we ask, where is this pressure? So, the pressure is defined at every point in the fluid, and of course, what we mean by a point, we just had a look at it, is that we mean an element, a hypothetical element in the fluid which has a certain minimum dimension. Smaller than that, we cannot talk of pressure. Larger than that, we can talk of pressure. So, that is the meaning of a point. That means, at every point, say the air in the room, we can define any point and say what is the pressure at that point. We can also define pressure at every point on the surface. So, this could be a surface of say water in a lake, and above that there is air. So, we can talk of pressure at the surface of this liquid. We can also, as we just saw, even if this was a solid, we can still talk of the pressure on the surface on the fluid side. And if the system is in equilibrium, we can say that the pressure at every point in the system is the same. However, if the system is undergoing processes, this may not always be the case, in which case we have to do a different type of analysis. Let us now look at the different definitions of pressure, and here we have two. First is the thermodynamic definition of pressure, and then we will look at the hydrodynamic definition of pressure. In the thermodynamic definition of pressure, we can go back and, at least for the sake of gases, to illustrate the point, we can look at the kinetic theory of gases. And what it says is that every gas, all the molecules that are there, they are always in random motion. They are colliding with one another and they are colliding with the walls of the container in which the gas is kept. They do not have the same velocity, but there is a distribution of velocity across all the molecules taken together. So, now let us look at one molecule and see what it does, and then we will expand that to every other molecule that is doing the same thing. So, what we have drawn here is this is a surface of the container, say, and we will look at one molecule which is over there and say, now this is going to be moving, it moves along this line and strikes the surface at this point. It undergoes a completely elastic collision and then gets out and moves that way. What it did is that because its velocity underwent a change, there was a momentum change associated with it. So, this is what one molecule would do with this surface. We could then look at other molecules and ask, what are they doing? And like this, on this surface at different points, there are lots and lots of molecules coming and impacting and going away. The net effect of all of them together is a momentum transfer, which manifests itself as a force. So, this force will have two components. One normal to the surface and one in the plane of the surface. This plane, the one in the plane of the surface, is what will cause the shear. Pressure is what this normal component does. So, on this little element, this we will call, say, area is delta A. On this particular force was acting, this we call delta F n, because this is normal, and this force is what is experienced over a certain period of time by all the molecules hitting this surface. And then we say that we define pressure as this force divided by this area, the normal force divided by the area, in the limit that this area goes to a certain minimum possible area that is essential for the substance to be a continuum. So, that is why this delta A star is there, it is the lower limit of assumption of a continuum. It does not go to 0. If it goes to 0 or even goes to the order of the mean free path of the molecules, this definition breaks down. So, this is a large number of molecules undergoing collision with the surface. So, this is what happens in the case of a real surface, and we can then expand this same concept to look at fluids. So, if the surface is fluid on a solid or fluid on a fluid. So, this surface that we have taken, we illustrated this by taking that this is a solid, but it could well have been, say, water surface looking a vapor or a gas. So, that is what the kinetic theory of gases tells us. If this instead of being a gas, it were a liquid, the treatment would be very much the same. There will be quantitative differences in various things that happen here. So, this would then define what is the pressure at a point on a surface, or the pressure exerted by a fluid at a point on a surface. So, that is what this definition would be. But how do we define pressure inside a gas itself or inside a liquid itself? So, that is what we are now going to look at by invoking the idea of a hypothetical surface. So, here is a little picture, and these are molecules, not necessarily all of the same type, and we say, well, I want to find out the pressure at this point. How do I do it? So, what we do is that out here we will take a hypothetical surface and do the same analysis as we did before, but in this case, because it is a hypothetical surface, these molecules will be coming here, they will be going through this. Similarly, ones coming here and going through this. Then we could argue there is no change of momentum. How do I talk of a force? So, what we do is we invoke that this surface is a hypothetical surface look at what are the molecules coming on it and treat this as a solid. And knowing the velocity vector of the molecules that are coming on it, we can then say what will be the velocity vector when they bounce off the surface, and from there we can calculate and estimate what is the pressure. So, then we come back to the same formula, and the definition of pressure then remains the same, that we take an element of area delta A there, and by doing this we figure out what is the normal force acting on it, and the ratio of that becomes our pressure. Now, here we have another flexibility. We could have taken the surface in any plane. It could have been like this, it could have been like that, or it could have been any orientation, and we could have defined the pressure. And if the motion of these molecules is perfectly random and it has no preferred direction, then we can conclude that at any point, irrespective of the orientation of the surface taken, the pressure is same in all directions. And that is what we have learnt in some other courses. So, that is what we are doing now with a hypothetical surface, and we invoke the concept from the second law of motion, and invoking the idea that the collision between a molecule and the surface is a perfectly elastic collision, which results in a change of momentum, which causes the idea of a force. So, that was the definition of pressure from the standpoint of thermodynamics. Now, we look at hydrodynamics, and this is what you would have possibly come across in a fluid mechanics course. And the approach to fluid mechanics is also continuum based, and it begins with by taking an element and defining the stresses acting on it. We are not looking at pressure anymore, we are now talking of stresses, and we define normal stress and the shear stress. So, these are the normal stress, say we can call it sigma x x, and there is a equal and opposite one coming here, sigma x x, and like this there is sigma z z, and this could be sigma y y. And the shear stresses, if we want to show them, there will be this and this on this surface, this and this on this surface, and like that we can add all those shear stresses. So, we have a total of 6 normal stresses and 12 shear stresses. The opposites are of equal magnitude, and so we generate a tensor which is a 3 by 3 matrix. So, this is a basic definition of any material, and it is not restricted to fluids, solids, or even viscoelastic fluids or anything else. With this, we can then go ahead and say, well, if it is a fluid, then we have to do a whole bunch of analysis, which we will not do in this lecture. And what it brings it out to us is that we get a term which is the average of the 3 principal normal stresses. So, 1/3 of sigma x x plus 1 sigma y y plus sigma z z. This is the hydrodynamic definition of pressure. This approach is completely different from the thermodynamic approach, and then one would ask, well, are the two related? Are the two the same? If so, under what conditions? And that, fortunately for us, what is nice is that in classical thermodynamics, as well as the same thing when we do in fluid mechanics, where also we have done the macroscopic approach, and we are relied on the idea of a continuum. Both these definitions of pressure have the same value. So, we do not have a problem, and that makes life a lot more convenient and easy for us. So, that is one important thing, that even though we have 2 conceptual ways of looking at pressure, in the applications that we look at, they both have the same value. So, that was all about the definition of pressure. Now, let us ask what are the units. In the SI system, the unit of pressure is the Pascal, defined as Newton per meter square. Also, we have the unit bar. 1 bar is 10 to the power 5 pascals or 100 kilopascals. And also, a unit often used is megapascal, and 1 bar is exactly 0.1 megapascal. So, this is one. A second unit that comes quite often is atmosphere. The definition of 1 atmosphere pressure is that it corresponds to 760 millimeters of mercury at 0 degrees Celsius at mean sea level. And this, if we do the calculation simply as rho g h, the international standard value of the atmosphere is 101,325 pascals. And this, in terms of force, becomes 1.033 kgf per square centimeter. So, this is another unit which has been in use for a long time, and a lot of people have an intuitive feel for it, but gradually everybody is moving to the SI system and looking at bar. 1 atmosphere has also been variously known as the standard atmosphere, but that definition has now changed. In 1982, the IUPAC decided that properties at standard pressure will correspond to pressure at 0.1 megapascal. So, if you see some older tables, those properties would be given at 1 atmospheric pressure. You look at newer tables, they will all be given at 0.1 megapascal. Another unit that has been in use is the technical atmosphere, ATA. This is also the same thing as 1 atmosphere or 1.033 bar. So, the technical atmosphere 1 ATA, this is actually 1 kgf per square centimeter. So, we have 1 atmosphere which is 760 millimeters of mercury, 1 technical atmosphere which is 1 kgf per square centimeter, and then we have the SI unit of bar. So, the SI system is completely independent of the fluid or the units or anything. It is a very robust definition. And in this course, we will be almost completely be sticking with SI units. Then at very low pressures, we come across another unit which is called torr. The torr is 1 torr is defined as 1 millimeter of mercury pressure. And if you want to calculate into pascals, we just do the rho g h calculation, h being 1 millimeter, and you can see how many pascal does this correspond to. So, those were the definitions and units of pressure. Now, we come to the real world and we see, well, how do I measure pressure, how do I report it, and when I measure it, what am I actually measuring? To understand that, we will begin with by first defining one term, the ambient pressure. So, the first thing is, what do we mean by the word ambient? Simply, when we say ambient or ambient air, it says that this is the air that is surrounding us, or if there is an instrument, what is the air that is surrounding that instrument. So, if we are sitting in a room, the air in the room, or if you are in a laboratory, the air in the laboratory, that is the ambient. If the instrument is in the laboratory, the ambient would be the air in the laboratory. So, the ambient can be characterized by pressure, temperature, then we can put other properties also, density and so on. In particular, ambient in general would vary with the time of the hour or day. So, it is not something which is absolutely constant at all times. Neither the pressure nor the temperature, or if you want to say how much moisture is there, say the humidity ratio and the density, all of these, they vary with time. The variation may not be very large, but strictly it is not constant. So, we cannot say that the ambient pressure is constant always at all places. That would be an incorrect statement. Looking at ambient pressure by itself, this is the pressure of the immediate surrounding air. So, what is it? If we are sitting there and we take a small element over there And so, this element, the surface, this could be a surface, say anything, a solid surface, there is no motion. What it feels is that because of the gravitational field all the way up, as long as there is a substance, this gravity field is causing a force on this, which is weight per unit area of this column. So, what we are saying here is that we are looking at an air column. We could do the same thing going inside the ocean. There it will not be air column, it is a water column, and of course, the big difference is that the density of water is much more than the density of air, and so you start seeing very, very large pressures. So, this is an example of deep sea diving robots or deep sea diving vessels, which have to withstand extremely high pressures acting on its outside. But the point is this, that the ambient is exerting this pressure on every surface. It is not just say the tabletop or one's body, or it is there on every instrument, on everywhere this pressure is coming. So, this pressure is the absolute pressure of the ambient air. So, what we defined so far, thermodynamic pressure, hydrodynamic pressure, those were the force exerted by the fluid on the surface, and that as the name absolute pressure. So, what we are seeing here is also the same thing, that this is the absolute pressure of the ambient air. And as I said, this is the weight of the air column above the surface, and it is possible because there is a gravity field. If we talk about the same thing going into the space station, where there is 0 or microgravity, this mode of a surface feeling the pressure does not exist. We would then be in a situation where we have a space where the only pressure that one would feel is the pressure of that gas or the air which is inside. Whatever its pressure is that is the pressure we will feel. Gravity is no longer influencing anything in such an environment. And of course, if you were to go to some other planet, say Jupiter, where that pressure is much greater, then of course, the ambient pressure will be very, very high. So, how do we measure ambient pressure? And this you might have learnt in school days. That instrument is called the barometer. The most reliable and the oldest instrument, still very good for all work, is the Mercury Barometer, where all one did was to take a tube longer than 760 millimeters, filled it with mercury and inserted it into a bath of mercury. So, the height that this stays at, this is your H, and rho g H is your ambient pressure. The space at the top here, vacuum. So, no pressure there. Vacuum is 0 pressure. So, pressure acting here is 0, pressure acting here is something, pressure here and pressure here have to be the same, and that is how we do the calculation. These days, we have pressure transducers of various types that sense the pressure, and depending on that pressure, they give a signal. That signal is proportional to the pressure, and a calibration curve is used to interpret that. And then we have the old instrument, the aneroid, which tells us what is the ambient pressure, and this is good enough that it even picks up changes in the pressure when there are humidity changes, and so this is a good instrument for weather prediction. But all these instruments are basically measuring the ambient pressure. One of the symbols used for that, some would call it PA, or we could call it PAMB, or we could just write ambient. So, that is first term that we come across, ambient pressure. And just to complete this discussion, we said that it varies with altitude, which is a very important thing, and if you make a plot where this side is the ambient pressure and this side is altitude going up to several kilometers, then we would see a curve which would go something like that, and after some point the pressure becomes 0. So, this is 0, this is also 0. So, at sea level this would be the value of the ambient pressure 101.325 kilopascal. You go to a altitude of about 5000 meters, somewhere around that approximately, the pressure there is roughly half of what it is at sea level. And you go to the top of Mount Everest, the pressure is even lower, which is roughly 1/3. And you go much higher, the pressures go very low. So, this has implications on many things, that people who are at high altitude regions, things just do not work out the same way as they would do at sea level. So, this becomes an issue. That it also influences, for instance, how a truck will drive. At sea level, air is much denser, at a higher altitude, air is much less denser, the engine will not produce that much power. So, that is the type of implications of this knowledge. Humidity influences the ambient pressure quite significantly, and we just saw that it is basically air which is O2 plus N2 as two ideal gases, into which we have put water vapor, and this makes a lot of changes to the way we look at the atmosphere. So, the ambient air has two important implications. In applications where ambient air is the working substance, for example, like an engine or an aircraft engine, we have to worry about these issues. We have to worry about altitude, we have to worry about its pressure, we have to worry about the temperature. All of this influences the way that machine will behave. In a more immediate way, the ambient pressure is essential, that in the lab when we measure an instrument or measure pressure using an instrument and we get some reading, that is not the absolute pressure, and to get the absolute pressure, to come from here to the absolute pressure, we need the ambient pressure. So, we need it in all calculations there. Now, we come to a quick discussion on how we measure pressure. The simplest, the most reliable instrument used for a very long time is the manometer. It has got two tubes, vertical tubes, they could even be inclined, connected at the bottom and filled with some liquid, which when both legs are open to the ambient, the level is the same. And now, two things can happen. So, this fluid could be mercury, water or alcohol, if the substance that is over here is air. If that substance is water, then we would put mercury and maybe leave one leg open. So, now what happens? Say this side there is pressure acting P1, this side pressure acting P2. If the two are equal, the legs are at the same position. But what if say P2 is greater than P1? This pressure is more, it will push this leg down. So, it will come here, this will go up that much. So, this is a level difference that we have, and we say that the pressure here and the pressure here is the same. Pressure here is P2, pressure here is P1 plus P1 acting on top of this plus the pressure here. So, we get P2 is equal to P1 plus say rho g, and this height is h. Now, the question is, we want P2, but for that we need to know P1. One way is say that, well, if I do not know P1, I will only report this as the pressure and say it is this much pressure above the atmosphere and get done with it. This is what we will in a minute call as a gauge pressure. But to get the absolute pressure, we have to know this value. And the easiest thing to do is to leave this thing exposed to the ambient, measure the ambient with a barometer or any other instrument, get that value, put it in here, do this calculation, add the two, and we get the value of the absolute value of the pressure at P2. Now, a second thing can happen here. Suppose now P2 is less than P1. Now, this leg will go up, this leg will come down, and now we have a pressure difference over there. This could be H. Now, we ask what is the absolute pressure in P2, and we say P2 is equal to P1 minus rho g H. So, like before, if we did not know P1, we could say that the pressure is this much below atmospheric pressure, or if P1 happened to be the ambient. So, this much below the ambient pressure. If we measure the ambient with a barometer or any other instrument, we can put that here, subtract this value, and we got our absolute pressure at P2. Very simple instrument, very easy to make, very reliable, very reasonably good for many applications. At very high pressures it does not work because the physical size of the tube becomes too big. Very low pressures you have difficulty using it. So, what we record when we see an instrument is not the pressure, but we record this level and we record the level when the measurement is being done. So, we are recording this reading number 1, which is same for both. Then we record this reading, say 2 in 2A over here, and we record this reading, this level, which is 2B. That is a primary data from a measurement, and we need to know what is the fluid, and using that then we calculate this, and this formula, what the way I have written it, I have assumed that this is a liquid or water, and the ambient means ambient air, and since the density of air is substantially less than density of any of these liquids, we are justified in writing this. But if this were water, in that case we would have to change this, and this rho would have become rho of the liquid minus rho of water. So, that is where the difference of density would come in. In most applications where we are looking at gases, this relation is good enough. Liquids, we must take care of the density difference. The next most popular instrument is called the Bourdon Gage, which has a tube like this, and here we can connect it to whatever whose pressure we want to measure. The cross section of this tube, if you were to cut like this, would look like this. So, this is the metal, inside it is hollow and it is closed at this end. What happens then? If we apply a pressure over there, or when there is say no pressure, then this tube has this particular position, this point is at this place, and through a mechanism it moves a dial on the gauge. That gauge is marked at 0. A pressure greater than atmosphere is applied. So, P applied is greater than P ambient. This tube inside pressure is more, so it will start to open up. This point will move over here. This motion is converted by a mechanism into motion of the dial, and now the dial pointer will point somewhere else. In the process of calibration, we apply known pressures over here, see where the deflection is, and put the markings at those points. So, a calibration is essential for Bourdon Gage. So, that is what we have put here. It is a hollow C-shaped tube, deflection of dial and pointer, and you have to calibrate it against a known pressure. So, what are we sensing here? When there was no applied pressure here, the pressure here was equal to P ambient, and the dial was marked at 0. So, it was telling you that the pressure inside is not 0, but the pressure inside is the ambient pressure. That is one thing. Second, when we apply this pressure and it changed, the deflection that happened on the outside, you have ambient acting, on the inside of the wall we had the applied pressure acting. The deflection that it produces is the net effect of the pressure minus the P ambient pressure, and so the marking on the dial, wherever the dial goes, the deflection that you see is proportional to P minus the ambient pressure. So, we are not measuring the absolute pressure. That is the important point, and this is what is classically known as, whatever reading comes out of it is called the gauge pressure, and we denote it by whatever number it was there, the units whatever they may be, does not matter, but after that we put G, explicitly telling that this is a pressure relative to the ambient pressure. If that G is not there, it automatically means it is an absolute pressure. A similar thing would be there, where some gauge could be calibrated if for working at pressures below atmosphere. Then too you will have the same thing, but now we will say that it is so many bar or so many millimeters of mercury, and we will say this is so many bar vacuum. The number comes there, bar vacuum tells you that this much pressure below the ambient. What you have measured was the gauge pressure. So, the pressure difference between the inside and outside produces the deflection. Inside pressure is equal to outside pressure, then the reading on the dial is 0. And that we have to add to the ambient pressure what the dial reading is, or subtract the dial reading from it to get the absolute pressure that we want. These dial gauges, Bourdon gauges are available very widely. There are lots of manufacturers, and you get a vast variety of these instruments, and one can pick up what type of a connection you want, what units it want, how big you want it, what is the accuracy, all those come in. So, they will come in all these types of units, and we can pick what we actually want for the application. And of course, as I have just mentioned, the pressure difference is recorded, not the absolute pressure. This is very, very important. In all practical work, laboratory work, we always end up measuring a gauge pressure to which we have to add the ambient pressure. So, what we have observed is the gauge pressure, not the absolute pressure. So, as I said, we put the G if it is above atmospheric pressure, or we write vacuum if it is below atmospheric pressure. So, please keep that in mind. It is a very, very important aspect of measurement, and after that, whatever calculations we do, we always have to use only the absolute pressure. Gauge pressure is of no use in calculations. These days, the most standard instrument has become the transducer, which has got one of the type is that you have a strain gauge mounted on the diaphragm, which deflects. So, you have a diaphragm there on which you have put up a sensor, which is a strain gauge, and this side it sees pressure P 1, this side it sees pressure P 2, and when they are equal, there is no deflection, there is a pressure difference, the diaphragm deflects, the deflection causes a change in resistance in the sensor, that causes a change in the signal, and we interpret that signal as a pressure signal. So, that is one of the types of transducers, diaphragm type. There are many other types, we will not go into the details on it over here, but the point is that we are measuring a gauge pressure. We need the ambient pressure to come to the absolute pressure. In some applications like flow meters, which use Venturi orifice or nozzle flow meter, we are measuring essentially a differential pressure, pressure difference between 2 points. So, that is a differential pressure measurement, and there the issue of gauge or vacuum does not arise, because the difference in pressure is what we are measuring. All transducers require calibration. This is a very important aspect. And I said, like before, gauge pressure is measured, not the absolute pressure. Add to that transducer some more electronics, and then that electronics generates a signal and transmits it. This can then be taken up by a data acquisition system and interpreted as to what the value is. Typical signals are in this range, 0 to 20 milliamperes or 4 to 20 milliamperes. And today, if you go to any process industry or even otherwise, these are very widely used everywhere now. So, everything that we did for a transducer is applicable here. In addition to that, there is some more electronics which we have to understand to fully appreciate what this device does. Then there are other pressure sensing devices. I am just listing it here. We will not go into any detail in it. If you are interested, you can read up. There is a MacLeod gauge, electronic gauges like the piezoelectric or piezoresistive pickups, capacitive pickups and magnetic pickups, low pressure gauges, Pirani and ionization gauges. So, the variety of instruments which are applicable for certain range of applications, and depending on one's requirement, you would have to pick up that particular instrument. Pressure measurement is subjected to various standards. Here are some of the important ones that I have listed. ASME Performance Test Code 19-2 tells us every aspect of pressure measurement. Similar details are given in ASTM B40.100 2013. Then there are European standards EN 472 and EN 837. Many manufacturers will tell you that we have made the instrument and it conforms to such and such a class as per say EN 837-1 or ASTM B40.100. So, that is all they will tell you, and if that is a lot of information, because if you open up the standard and figure out what that was, you will learn lot more things coming out of that. There are similar Indian and international standards. It is good to know that all these are there, because in the practical world, this is how the world operates. Now that we have already talked about absolute pressure, we say that this is nothing but the thermodynamic pressure. It is always a positive number. If there is 0 pressure, it means there is vacuum. There is no substance in it. And absolute pressure can be indicated by any of the units that we have seen before: bar, millimeters of water column, megapascal, and even the units which are much less in use, but still a lot of people use it, kg per square centimeter, which is same as kgf per square centimeter, and some older ones still use pounds per square inch, psi, but that is of course now largely outdated. Absolute pressure is very crucial, because everything we will learn in this course in thermodynamics, all the pressure related calculations, they all are based on absolute pressure. So, whenever a problem comes your way or you are looking up data from tables, whenever it says pressure, we by default mean it is absolute pressure. So, that is what our interpretation here will be. We say pressure, it means absolute pressure. All property data that we get, and we will use lots of property data throughout the course, they all are absolute pressures. For example, say steam tables or properties of refrigerants, everything is there. And something to keep in mind, all these property tables give the answer to a certain number of significant places. That tells you how good or accurate that measurement is, and essentially tells you what is the uncertainty in that, what level of uncertainty to expect in it. Some examples of absolute pressure: it could be 5 bar, 67.2 kg per square centimeter, 10 millimeters of mercury absolute, 12.8 megapascal. Just by looking at these numbers, it should immediately be clear to us we are looking at absolute pressure. On the other hand, gauge pressure, what we got from reading in the laboratory, we have to add or subtract the ambient pressure to it. So, gauge pressure for pressures above ambient atmosphere and ambient pressure is the absolute pressure minus the ambient pressure. So, we will always put the letter G if the pressure is greater than ambient. We will always write vacuum if the pressure is less than ambient pressure. So, we will record it as the units with a G or mmWc or millimeters of mercury or vacuum, or even sometimes even a negative pressure. So, here are some examples. 5 bar gauge, the absolute pressure is 5 bar gauge plus the ambient pressure, 67.2 kg per square centimeter, 74 millimeters of mercury, 12.8 megapascal. These are all gauge pressures above atmosphere, ambient, and if it is below ambient, 110 millimeters of water column vacuum or 0.1 bar vacuum or minus 0.17 bar. Of course, a negative value or vacuum value cannot be less than P ambient. So, if we see somebody saying the pressure is minus 2 bar, you know there is something absurd, it does not make sense. So, if the pressure is greater than ambient, we take the gauge pressure and add the ambient pressure. If pressure is less than ambient, we take the ambient pressure and subtract the gauge pressure from it. This is our central idea. So, here are some more examples. 5 bar means absolute pressure is 5 bar, 7 bar gauge means absolute pressure P is 7 bar plus P ambient, minus 0.5 bar means ambient minus 0.5 bar, and so on. 174 millimeters of mercury vacuum means pressure is 174 millimeters of mercury below ambient pressure. Now, we look at some variants of pressure. In thermodynamics, whenever we talk of pressure, it means static pressure. Whether we measure it as a gauge pressure or an absolute pressure, it is a static pressure. So, for example, if this is a tank which has got some substance in it and we are measuring the pressure with a Bourdon gauge, we are getting the static pressure, which for us is also the thermodynamic pressure. If the fluid is moving, say for instance, here the fluid is in motion this way, then we can make a hole like this and connect it to an instrument or a transducer and measure it. This will also give us the static pressure, which is also for us the thermodynamic pressure. However, if we put something which is like this, it is looking at the fluid coming onto it, but of course, it is closed at the other end. This will not measure the pressure, it will measure the total pressure, which is the static pressure plus the dynamic head, and the dynamic pressure is just half rho v square. So, unless we explicitly state this, we will not be looking at it. All of this is required a lot more in fluid mechanics. Later on, we will come across some more terms. I will just quickly list it here. Reduced pressure, we will come later on. Reduced pressure is pressure divided by critical pressure. Relative pressure is defined as PR e to the power S0 by R. S0 is this standard state entropy, R is the gas constant, C is the another constant. Then we will also come across stagnation pressure in some applications. This is the pressure that a moving fluid will attain if it is brought to rest isentropically. So, this is the pressure when H0, which when the fluid is brought to rest, is equal to what the fluid had when it was in motion. For an isothermal system, this becomes equal to P0 is P plus V square by 2, and this is what you would see very often in fluid mechanics. Then there are other terms that will come. In mixtures of gases, we will come across partial pressure, where the Dalton's law of partial pressure tells us that this is the pressure exerted by a component of a gas in a mixture of gases if it were alone present in the total volume at the same temperature. Then we have hydrostatic pressure, largely coming in fluid mechanics, that the fluid is at rest or at constant velocity and there is a gravity field, then at any point the pressure is rho g h. And this includes multilayer fluids and also is the case where you have water on top of which is the atmosphere. Back pressure is a term that is used to denote the exit or exhaust pressure of a turbo machine. Then there are things like net positive suction head, which is applicable for pumps, and pressure drop and system resistance, which are applicable for flows in pipes and ducts. So, these are again largely related to fluid mechanics, but again they are all part of the same family related to pressure. Now, we will look at temperature. Like before, it is also applicable for a continuum, but unlike pressure, there is a big difference here that temperature can be assigned to any material, fluid, solid, even at the surface. There is absolutely no restriction on whose temperature we are looking at. We can talk of a temperature of a system or a substance provided it is in thermal equilibrium. Temperature for any system or any substance is defined at every point on the surface, and when we say every point, it is every point inside the system. It may be the same, it may be different, but it is defined everywhere. So, what is temperature? It is a measure of the internal energy of the molecules of the substance. Now, the question is, and we will see later in the course what is internal energy, but very quickly, energy of a molecule in any phase, solid, liquid or gas, is its energy that it possesses by itself due to translation motion, rotational motion and vibrations. This is not the bulk velocity. When we say that air is moving at 5 meters per second, that is not part of this. So, what we have done is we have looked at some things at a microscopic level, but said that now I will do that for every one of these molecules in the system, average it out and assign a particular property to this entire domain to get a macroscopic property, which we will call the temperature. So, this has a one-to-one correspondence with energy of molecules, and energy is the internal energy of the molecules. Then we look at what is thermodynamic temperature. The thermodynamic temperature is the same as the absolute measure of temperature, and the absolute means that the lowest that we can get in this is 0. In the absolute sense, there will never be a negative temperature. So, you have absolute 0, the units are Kelvin, and so absolute 0 is 0 K, 0 Kelvin. There can never be minus something Kelvin temperature. And that comes about from the third law of thermodynamics that you will study later in the course, that entropy of a perfect crystal is 0 at absolute 0, and that gives us the basis for absolute entropy, but it does not tell you what the value is. We can then work out and say that at absolute 0 we can assign entropy 0 for convenience sake. We could have assigned 10, 20, 30, any of those. So, that tells us what is the thermodynamic temperature. But then how do I measure it? And for that we require yet another concept which comes from the Zeroth Law of Thermodynamics, which says that two bodies have equality of temperature with a third body. They in turn have equality of temperature with one another. So, here you have a body in equilibrium with this thing, then you have another body which is independently in equilibrium with this. So, if we can calibrate this with this device and assign it some temperature, and then use that to figure out this temperature, then we can be sure that what we had this temperature is the temperature of this substance. So, it looks like a very simple and obvious thing, but it has considerable impact on how we actually play it out. Now, we look at the thermodynamic temperature scale, and we invoke this here because this is an important concept that now we will no longer talk of the substance. So, we will not say that this substance in this state has this temperature. The thermodynamic temperature scale is independent of the substance, and later on in the course you will come across the reversible cycle and the Carnot cycle, which says that the thermal efficiency of a reversible cycle is only a function of the two temperatures with which it exchanges heat. So, QH by QL of a reversible cycle is some function of TH divided by the same function at TL, and for the simplest case we have this as TH by TL. So, this gives us a basis for absolute temperatures. Finally, how do I put numbers on temperatures and say this is the correct number? For that, we have an international standard called ITS 90, which is the International Temperature Scale 1990. According to this international standard, which now the whole world follows, we also do that. 1 Kelvin is 1 by 273.16 of the thermodynamic temperature of the triple point of water. So, this is now our definition. And then we define the Celsius scale, the international Celsius temperature, as the Kelvin temperature minus 273.15. So, two important things have come out. We defined what is 1 Kelvin and how is the temperature, international Celsius temperature scale related to the absolute temperature scale. And what the ITS 1990 does, that for different ranges of temperature, it gives us the basis and its equations for calculating the temperature. The four broad categories are from 0.65 Kelvin to 5 Kelvin, we can measure the pressure of helium vapor and calculate the temperature from there. The ITS 90 gives us the equations for doing that. 3 Kelvin to 24.5561 Kelvin, this is the gas thermometer, again of different types. They also give us the equations for using it. 13.8033 Kelvin to 961.78 degrees Celsius, we can convert this into Kelvin. We have the platinum resistance thermometer, something we will also be used in the lab. What it does is that we take a certain wire of platinum of a particular quality, and all sorts of heat treatment that have been done to it, and assign it 100 ohms resistance at 0 degrees Celsius. And then this is calibrated that at different temperatures this has got different resistances. So, in an experiment using this instrument, we measure the resistance, then using this table we go back and figure out what the temperature is. So, this is a very robust, reliable, accurate measurement technique, widely used, also known as the platinum resistance detector or platinum resistance thermometer or the resistance temperature detector RTD. So, this is a very broad range, and you can see we can use this in many of the things we work with. And for temperatures greater than 961.78 degrees Celsius, which by the way is the freezing point of silver, we have Planck's radiation law. So, this is what we have, the ITS 90 definition, and as you can see here, temperature is given with 6 significant places. In a practical sense, we will never ever be able to measure anything that accurately. Even 2 places of decimal in temperature measurement is a very big achievement. We would be quite lucky to be very confident about the first place after decimal. Just to complete this ITS scale, these are the various substances and its state and what is the defining point for that temperature. We have triple point of hydrogen, which has been given certain temperature. Here you can see we have triple point of water, melting point of gallium, indium, then you have melting point of silver, gold and copper. So, what one can do is that if we want to generate a temperature which is very accurately known, we can use one of these things. Triple point of water is the easiest thing to do, is to get ice and water, crush it, put it together in a thermos flask and we produce that temperature in the laboratory. Very easy to do it, very reliable, very standard method. The various instruments available for temperature measurement, there is a thermocouple, which relies on the fact that dissimilar materials when put at different temperatures will produce an EMF. RTD we have just seen. Then thermistors, which is a negative temperature coefficient sensor. Platinum resistance thermometer or any other metal, T increases, its electrical resistance increases. In the case of thermistor, as T increases, its electrical resistance decreases. Then we have a variety of infrared non-contact thermometers, infrared cameras, and many more things here. So, on that note, we complete our discussion on pressure and temperature, and to summarize, we have said that pressure and temperature are macroscopic properties not assigned to a molecule, but to a minimum size of the material, which is told us by the continuum approach. So, they are macroscopic properties. They are very important properties because these can be measured, and from here we can calculate many other properties that we use in thermodynamics. For pressure, we said that it is applicable only for fluids. At most, we can define pressure on the solid fluid interface on the fluid side, not on the solid side. Then we looked at what is ambient pressure, we saw what is absolute pressure and gauge pressure, and what is the relation between these three. This is fundamentally important to all practical work. We also looked at various types of pressures and their definitions, and saw that this has also got a commonality with fluid mechanics, and we said that static pressure is what we mean by our thermodynamic pressure. Then we went through a quick list of instruments for pressure measurement. Then when we looked at temperature, we saw what is the thermodynamic temperature scale, what is its basis, and that the units are Kelvin, and how the zeroth and the third laws of thermodynamics help us to do that. Then we saw that we have defined something called absolute zero, and then we saw that we have an important thing, which is the ITS 90, the International Temperature Scale of 1990, which is the global standard for all temperature measurements. And finally, we looked at various instruments which we can use for making temperature measurement. So, with that we conclude this lecture. Thank you.